This is the first section of chapter 5 and it's about estimators, bias and standard error. So this section is all about how we can estimate an unknown population parameter. So e.g. something like the mean, the variance or the standard deviation. So our first step, if we want to estimate this unknown population parameter, is we start by taking a random sample from the population, and these here represent random variables, so our first sample, our second sample, our third sample, and so on. And so we're going to have a sample size of n. We have n observations. We can refer to them as x sub I, where the observations, each one of these observations are independent, so they're independent of each other, and they all have the same distribution. So for example, if one of these random variables is normally distributed, then all of them are going to be normally distributed. Then once we've got our random sample, then we do some sort of calculation on our random sample to generate what we call a statistic, and we use the letter T to represent that. So here T, our statistic, is some sort of function on our random variables. Now that may be something like the sum of our random variables, just add them together, the average of the random variables, add them together, divide by the number of random variables we've got, divided by n. It could be the difference between the largest and the smallest random variable, the maximum value of the random variable. So some sort of calculation that we carry out, but it's important that a statistic will not be calculated from, that should say from, an unknown population parameter, from unknown population parameters. So we cannot generate a statistic, for example, using mu, the population mean or the population standard deviation or variance, only some sort of function, some sort of calculation on our random sample only, so no population parameters. Now when we take multiple samples, in fact when we take all possible samples, then the values of t that we calculate by doing some sort of function on our sample will form what we call the sampling distribution of t, also known as the probability distribution of t. So a special case, an example of this is the sample mean. So the sampling distribution of the mean of our samples is normally distributed, where the mean of that distribution is the population mean, and the standard deviation of that distribution is the standard deviation, the variance of the population over the sample size. And this is what we call the central limit theorem. So you would have come across that before, and also you would have used this in the normal distribution chapter in the applied book year 2, where you're doing a hypothesis test to see whether the population mean has changed by looking at the mean of the sample. So basically we've taken lots of different samples, we've worked out the mean of those samples. Those means are all going to be slightly different, but what we will find is that they will be normally distributed. So the central limit theorem has sort of a point to play in this section. Now we can use a statistic t to estimate a population parameter, and we'll use theta to represent a population parameter, so that could be the mean, standard deviation, variance, whatever it is. And if we do that, in this case, we call t an estimator. Now, a particular value of t calculated from a single sample is called an estimate. And probably what we want to do is to take lots of samples, find lots of different values for t, find lots of different estimates, so that we can then do some sort of calculation to find an estimator. Now, if t is used as an estimate for our population parameter at theta, and the expected value of our statistic e of t is equal to that population parameter, in other words, we have worked out these different values of t, and we work out, well, what's the expected values of those, and that will equal the population parameter. Then t is what we call an unbiased estimate for our population parameter, an unbiased estimate for the population parameter. So here's an example. The expected value of the sample means is equal to the population mean. Now, it may be actually that when we work our estimate, that it's actually not equal to the population parameter, it's slightly off, in which case we've got something called a bias. So if t is used as an estimate of our population parameter, then the bias is equal to the expected value of our statistic minus the population parameter. So we're expecting a difference between the two. Now, if our expected value of our statistic minus the population parameter equals 0, then in which case the estimate that we've worked out will be unbiased. So we're back to this previous bullet point here. So we're back to this one. Next, we're going to look at ways of estimating the population variance, and an unbiased estimator for the population variance is a sample variance which is equal to 1 over n minus 1, where n is the sample size, times by the sum of x squared minus n times by our sample mean squared. Now, there are different forms of this formula. This one is probably the easiest one to use, and when we've got bigger n, it's going to give us a better estimate for our population variance. So bigger n is better. Then lastly, we can work out the standard deviation of an estimator, and we call this the standard error. Now, we can work out the standard error for our sample mean. That is how good our sample mean is in terms of estimating the population mean, and the standard error is the standard deviation over the square root of the sample size, or the standard deviation of our sample. So this would be the population standard deviation, if you know it, or the sample standard deviation, again divided by the square root of n. And here we can see that n is bigger. So as our sample size increases, we're going to get a better estimate for the population mean from our sample mean. As we can see that as n increases, our standard error is going to decrease. Example 1, a sample x sub 1, x sub 2 up to x sub n, so n units in my sample, is taken from a population with unknown population parameters mu and sigma. So we do not know the population mean, and we do not know the population standard deviation. State whether or not each of the following are statistics. So we'll look at A. Now, what do we do with A? We take 3 items from our sample, we add them together and divide by 3. So we're basically finding the mean of 3 items from the sample, no population parameters. So yes, it is a statistic. Then B, what we're doing, we're working out the maximum value of units from our sample. And again, this does not involve any population parameters. So the same answer, yes, it is a statistic. Remember, it's just some sort of function carried out on values from our sample. And C, now C involves unknown population parameters. So it's not a statistic. So no, it is not a statistic, since it uses unknown population parameters. And those unknown population parameters that it uses are the mean, the population mean, and the population standard deviation. Example 2. The weights in grams of a consignment of apples are normally distributed, okay, with a mean mu and a standard deviation 4. A random sample of size 25 is taken and the statistics R and T are calculated as follows. So R is going to be the difference between the weights of two apples, basically the last and the first apple from our sample of 25, and T is going to be the weight of all 25 of those apples. And we need to find the distributions of R and T. So let's start by writing down what the sample is, and the samples are these 25 apples. Okay, so all the way up to x25. So there's our sample. And we also know that the weight of any apple is normally distributed with a mean mu and a standard deviation of 4. So that's a variance of 4 squared. So what we can do to help us answer this question, we can use these results from chapter 4 where we've got combinations of random variables. So let's start by looking at the statistic R. And we can see from R what we're doing is we're subtracting one of the random variables from the other. So we're going to be using this rule here. E of x minus y is going to be E of x minus E of y. So this is what we're going to use to find the mean. So R is going to be normally distributed. And the way that we find the mean of this distribution, so using this information here in this rule, so it's the mean of x minus the mean of y. Now the mean of x is mu, the mean of y is going to be mu. So you could imagine x and y here just being one value of x, xi, and this being a different value of x, xj, or something like that, but any two random variables, two apples. And then to work out the variance that goes here, we can use this rule here. So we've got the variance of one apple minus the a different apple. So that's going to be adding the two variances together. So it's going to be the variance of one apple plus the variance of another apple. So all we need to do is just simplify this. So R is normally distributed with a mean of 0 and a variance of 2 sigma squared. Now in this question we know that the variance or the standard deviation is 4, so the variance is 4 squared. So we can now just replace the sigma squared with 4 squared. So we've got 2 times by 4 squared, which is going to be 2 times by 16, 32. Or we could write this as 2 times, root 32 squared, because that's the normal way that we write it. But writing like this is fine. Now we'll look at the statistic T. Now for the statistic T, what we're doing, we're adding all 25 weights together. So we can use this rule here, where we've got the sum of n number of random variables. So in this case, it's going to be 25 of these random variables. So T is going to be normally distributed. Since n is 25, we're going to have 25 mu. And then here we're going to have 25 sigma squared, 25 times the variance. Now the variance is 4 squared. So we'll just simplify that a bit. And we'll have 25 mu. So that's 400. So again, we could write the square root of 400 squared, so we could write this as 20 squared instead here. Example 3. A large bag contains counters. 60% of the counters have the number 0 and 40% have the number 1. And what we need to do in part A is find a population mean and a population variance of the values shown on the counters. Okay, so this is discrete distribution, and X in this case is just going to stand for the number shown on the counter, and because it's a discrete distribution, we'll have our probability distribution like this, where our outcomes are 0 and 1, and the probabilities of those are 0.6, 60%, and 0.4, 4%. The population mean is E of X, the expected value of X, so 0 times by 0.6 plus 1 times by 0.4, which just gives 0.4. And then our population variance is equal to var X, so it's going to be E of X squared, so 0 squared times by 0.6 plus 1 squared times by 0.4 minus E of X squared, so we want to subtract E of X squared, and that gives us a value of 0.16. Okay, right, let's move on to part B. And part B, it says list all the possible observations from this sample. And it would help to read this bit just before. It says a simple random sample of 3 is taken. Okay, so we need to list basically all the possible observations when we take 3 counters. We'll do this systematically. So they could all be zeros, or one of them could be 1, that last one. Actually may help if I put them in brackets rather than have commas all over the place. I'll have the commas as well. And I'm just going to go through it systematically. So next one, 0, 1, 0, and then 1, 0, 0. So I'm listing all the ones that have just got one of the counters is a 1. Then I'll carry on the ones where 2 of the counters are 1s. So that will be 0, 1, 1. 1, 0, 1, and then 1, 1, 0, and then the last one is where all 3 are 1. So it looks like I've got 1, 2, 3, 4, 5, 6, 7, 8 different outcomes, which is what I was expecting. Moving on to part C, it says find the sampling distribution for the mean, and that is where we add the sum of the 3 counters and divide by 3. Now another name for this is the probability distribution, and basically we want a table similar to this, but the top row of our table is going to contain X bar, all the different means possible, and the bottom row is going to contain the probability of getting those different means. Right, so if we go through these, the different means possible where we can get a mean of 0 when we get all zeros on our counters. If we just get a single 1 on our counter, so we add those up and divide by 3, we're going to get a mean of 1/3. If 2 of the counters have 1 on them, so these 3 cases here, that will give us a mean of 2/3. And then the other option is that all 3 of the counters have a 1 on there, and that gives a mean of 1. So they're the different possible values we can have for the mean. We're now going to work out what's the probability of getting these different means. Okay, let's work these out then. So when am I going to get a mean of 0? going to get a mean of 0 when all three counters come up on 0. And what's the probability of that happening? Well, if the probability of one counter coming up 0 is 60%, 0.6, then the probability that all three counters come up with 0 is going to be 0.6 cubed. Now, if I do this on my calculator, it comes up with 27/125. So I'm going to keep it as that, 27/125, rather than fiddle around with fractions. So we're going to get a mean of 0 when they all come up with zeros on the counters. Now, to get a mean of a third, one of the counters needs to come up with a 1 on it. What's the probability that one of the counters is going to come up with a 1 on it? I'll do the working down here. Well, that's going to be 2 of them come up 0, and one of them comes up 1. But that can happen in two different ways. So 3 ways. So I need to multiply that by 3. There's 3 ways in which I can get a 1 come up on the 3 counters, just 1, which means the mean is going to be a third. And on my calculator, that comes up as 54/125. 54/125. When am I going to get a mean of 2/3? When 2 of the counters come up with 1 of them, or a 1. So that's going to be 0.6 times 0.4 times 0.4. And how many different ways can I get 2 of the counters come up with a 1, 1, 2, 3. So I need to multiply this by 3. And that gives me 36/125. And I suppose I could just subtract these all from 1 to work out the remaining one. But I'm going to get a mean of 1 when all 3 counters come up with a 1 on them. And that's going to happen when we've got 0.4 cubed. And that gives me 8/125. So this is my sampling distribution or probability distribution for the mean. Okay, and you can see it's the same type of table that we had in part A, except our value here is not x, but x bar, the mean. Now part D, hence find the expected value for x bar for the mean and the variance of the mean. And we can work that in the same way that we've done before. So E of x bar is going to be 0 times by 27/125 plus a third times by 54/125 plus 2/3 times by 36/125 plus 1 times by 8/125. And that gives us a value of 2/5. And then the variance of the sample means is going to be 0 squared times by 27/125 plus a third squared times by 54/125 plus 2/3 squared times 36/125, put some brackets here, plus 1 squared times by 8/125, and we minus the mean squared, so we minus 2/5 squared, and that gives us a value of 2/25. So I'm just going to put the answer over here, so I've just got a bit more space. So the expected value for the sample mean is 2/5. The variance of this sample of 3 mean is 2/25. So we'll just get rid of this here. Part E, what we want to do is to find the sampling distribution or the probability distribution for the sample mode M. So here's my table here. Now in terms of the mode, when we've got 3 counters, most of the counters are either going to be zeros in these cases here, or in these cases here, most of the counters are going to be 1. So the mode can only ever be 0 or 1. What we need to do is to work out what's the probability that the mode is going to be 0 or the mode is going to be 1. Now, the mode is going to be 0 in these cases here, the ones that I'm highlighting in yellow. Okay, and what's the probability the counters are going to come up like this? Well, we've done this already. We know that the probability that they're all going to be zeros is this, 27 over 125, and then for these three, 54 over 125. So all we need to do is to add those probabilities together. So in these cases here, the mode is going to be 0. So 27 over 125 plus 54 over 125 is 81 over 125, like that. Okay, so I'll just sort of color code it so you can see. Oops, with a highlighter rather than a yellow pen there. And then for these ones here, okay, the ones I'm doing in blue, these are the ones where the mode is going to be 1. What's the probability of these happening? Well, it's going to be this one here, the 36 over 125 plus 8 over 125, and that's going to give us an answer of 44 over 125. Okay, probably won't highlight that in blue. That's probably not a good idea because since it's a blue pen, so let's maybe change these to green, and that would be a bit more helpful. Okay, it just lets you see where these values have come from. We don't need to work them out again because we worked them already in the previous part. And then lastly, part F, what we want to do is to find E of M and var M. So E of M, 0 times by 81 over 125 plus 1 times 44 over 125. That's just going to be 44 over 125. And then var of the mode, that's going to be 0 squared times by 81 over 125 plus 1 squared times 44 over 125, and then we minus the mean squared, so we minus 44 over 125 all squared, and that gives us 3564 over 15625. We probably want that as a decimal, so 0.22896. So 3 significant figures is fine. So we'll just highlight that answer. So these are 2 answers here. Now, before we move on to the next example, it might be worth just looking at what we calculate the population mean and variance and what we got for the mean and variance using the sample mean and the sample mode. Well, actually, using the sample mean, we got the same values. 2 over 25 is 0.16. So this would be a good estimator for the population mean and variance if we didn't know it using the sample mean. However, if we were to try and use the sample mode, you see these values are different. These are biased estimates. This is an unbiased estimate here. Example 4. A random sample, so x sub 1, x sub 2 up to x sub n, so a sample size of n, is taken from a population with x normally distributed and a population mean of mu and a population variance of sigma squared. Show that E of x bar equals the population mean mu. So in other words, if I were to take every possible sample and I was to work out the mean of those samples, and I basically were to work out the mean of all of those means, the expected value of all of those sample means, that would be the population mean. And we saw that in the last example. We worked out the mean from all of the different possible samples, we worked out the expected value of all of those means, and it equaled the population mean. I think it was something like 2/5 in that. But here we want to prove it algebraically. So first of all, we're going to start by saying, well, how do you find x bar? Well, you find x bar by adding together all of your random variables and then dividing that by n. So that's how we find x bar. So now we want to find the expected value of all of these sample means, which is finding the expected value of what we've got on the other side. So it's just like an equation. Whatever we do to one side, we do to the other. So we've got that there. Now we can use this rule here, E of AX equals A times E of X, where A is 1 over n. I could have written this by all of these together in brackets times by 1 over n, which would be like the A part here. So that can go to the front. So now this becomes 1 over n, and then times by e to the x. So that's going to be x1 plus x2 plus x3 up to xn. Next I can use this rule here and actually separate all of these out. So I now have e of x1 plus e x2 plus e x3 plus all the way up to e xn. We can now use this bit of information here that e of xi equals the population mean, since all of the random variables are normally distributed with a mean of mu. So each one of these here can be replaced by mu. So I have 1 over n times by mu plus mu plus mu right up to the last mu. And there's going to be n lots of those, isn't there? Because I've got n lots of samples. So it's 1 over n times by n lots of mu, and the n's cancel out, just leaving you with mu. So we can say, so e of x bar equals mean as required. So that means the mean of our sample means is equal to the population mean. Example 5. A random sample, x1 to xn, is taken from a population where x is normally distributed with a mean of mu and a variance of sigma squared. Show that var x equals sigma squared over n. Now, in some ways, this is similar to the previous proof. So we start by saying, well, how do we find x bar? Well, that's going to be by adding all of our random variables together and dividing by n. Now we basically do the variance to both sides. So that's going to be var of all of this stuff here, all our random variables added together, divided by n. So we can use this rule now, var of ax, where a is like 1 over n. I could have written this as 1 over n times the sum of all of these, equals a squared var x. So this can be written as 1 over n all squared, which is going to be 1 over n squared, times by the variance of the sum of these random variables. Now I can use this rule here basically to separate out all of these variances. So 1 over n squared plus or times by the variance of x1 plus variance of x2 plus variance x3 plus all the way up to the variance of xn. Then we can use this rule here to say that the variance of each one of these is going to be equal to the population variance, since they're all distributed that way. Each one of the random variables has a variance of sigma squared. So that means that I can replace each one of those variances with sigma squared, and I'm going to have n lots of all of those sigma squared, and then one of these n's is going to cancel out, leaving 1 over n sigma squared, or sigma squared over n as required, which basically means I can use the variance of the sample means to find the variance of the population if I times both sides by n. So n times by the variance of the sample means equals the population variance. So we're using our mean, our sample mean, to calculate a population parameter, the variance. Okay, example 6. The table below summarises the number of breakdowns x on a town's bypass on 30 randomly chosen days. And the table is here. I mean, to start by calculating unbiased estimates for the mean and variance of the number of breakdowns. Okay, now to make this easier, we're actually going to use our calculator to calculate like our summary statistics. So I've got the instructions here. You need to make sure that frequency is on, because it's like a frequency table here, and I've given instruction in blue on how to do that. Once you're sure that frequency is on, these are the steps you need to go through. At this point here, this is where you type the data in, and then after you've pressed 3, you're going to get all your summary statistics here. Now, even though we're using a calculator, we do need to show our working. Okay, so we want an unbiased estimate for the population mean. Now, this is a symbol for the population mean, but to show that it's an estimate, you put this little hat on it. So when you see that, it means that it's an estimate for the population mean. And our unbiased estimate for the population mean is going to be the sample mean, x bar, and that's equal to the sum of x over n. Now, because we've typed this in on our calculator, it actually gives us the value of x bar, 5.3 recurring, but we do need to show our working. Sum of x, that's given on our calculator, which is 160, and n, which is on 30 days. So 160 divided by 30, and then we can write down the answer for our calculator. Okay, so do show your working. Next, we're going to calculate an unbiased estimate for the population variance. So again, the little hat here tells us that this is an estimate, and to find the estimate, we're going to use the formula where we're going to use our sample to calculate an unbiased estimate. That's 1 over n minus 1 times by the sum of x squared minus n times by x bar squared. Okay, there are other forms of this formula, but this is the one that's going to be most useful. So now we can just plug the numbers in. So it's going to be 1 over n minus 1. Now n is 30, so it's going to be 29, 30 minus 1, times by the sum of x squared. Now the calculator tells me that the sum of x squared is 990. So this is from my calculator, so I don't need to calculate that. So it's going to be 990 minus n, which is 30, times by the mean squared. Now that's going to be this value here, so I'm going to put the exact value in. So times by, just got enough space, 160 over 30, and that's all squared, and we'll see what that gives us. Now that gives me exactly 410 over 87. If I use the SD button, that gives me 4.7126. So let's call it 4.71, 3 significant figures. Now you'll actually see that's given on the calculator. It will say S squared, and like the X looks quite big, but it's meant to be like a little X like that. So we could have just written the answer down from our calculator, but we do need to go through this process of writing down the working, and then we can use our calculator basically to check our answer. Now it says that 20 more days were randomly sampled, and this sample had X bar equal to 6.0 days and the variance as 5.0. Treating the 50 results as a single sample, obtain further unbiased estimates of the population mean and variance. So what we need to do is to combine the results for 20 days with the results for 30 days. So we know that X bar for the 20 days was 6.0. And we know that the way that we find X bar is the sum of X over N. Now we want to work out what the sum of X is. So if we do N, which is 20 days, so if we do 6.0 times by 20, we'll get this sum of X for these 20 days. So that's going to be 120. Now what we need to do is to add this sum of X with the previous sum of X. So we've now got the new sum of X as 160 plus 120. So that's going to be 280. Okay, so this represents the sum of X for all 50 days, the 30 and the 20. We now need to work out what the sum of X squared is, or sorry, what X squared is for all 50 days. Sorry, the sum of X squared for all 50 days. So first of all, we need to work out what's X squared for these 20 days that we've got. So we're going to use this formula here because we know this is equal to 5. So we can write 5, which is S squared, is equal to 1 over N. So we're now looking at the 20. So 1 over 20 minus 1, 19, times by the sum of X squared. So that's what we're trying to find, minus N, and N in this case is going to be 20, times by the mean squared. Now the mean is 6, so that's going to be 6 squared. So all we need to do now is to rearrange this to find the sum of X squared. So we would times both sides by 19, and then we would add 20 times by 6 squared, and that gives us a value of 815. So this is the sum of X squared for the 20 days. The sum of X squared for the 30 days is 990. So my new sum of X squared for all 50 days, let's spell new right, is going to be 815 plus 990, and that gives us 1805. And it's these values that I can now use to work out estimates for the unbiased estimates for the mean and the variance for now a sample of 50 days rather than 30. So starting with my new mean, my new X bar, which is going to be my new sum of X, 280, divided by the combined number of days, 50. So I'll do 280 and divide that by 50, and I get 28 over 5. The SD button, 5.6, so that's fine. And then my new variance is now going to be 1 over n minus 1. Now n is now 50, so 1 over 49 times by my new sum of x squared, which is 1805, minus n, which is now 50, times by my mean squared, so that's going to be 5.6 squared, and we'll work out what that gives us. And we get 237 over 49, and to three significant figures, that's 4.84. So we're sort of running out of space down here, so I'm going to write all the answers at the top before we carry on. Okay, now part C says find the standard error of this new estimate for the mean. So that's going to be this estimate that we've got here. Now, to find the standard error, the formula is going to be either standard deviation over the square root of n, or the sample standard deviation over the square root of n. Now, we don't know the population standard deviation, so that means we're going to be using this form here. So our estimate for S will be, and I'm going to use the exact value, that was the 237 over 49. So it's going to be the square root of that, square root of 237 over 49. And then all of that needs to be divided by the square root of n. Now n is 50, so we divide by the square root of 50. Now that gives us an exact value of square root of 474 over 70. Now if we press the SD button, I'll get 0.311, and that's to three significant figures. And lastly, part D, estimate the size of the sample required to achieve a standard error of less than 0.25. So our standard error is S over root n, and we want that to be less than 0.25. So this question is all about finding out n. So before we stick any numbers in, let's rearrange it to make n the subject. So we can have S over 0.25 is less than root n, and I'll flip it around and square both sides. So I'll have n is greater than S squared over 0.25 squared. Now we know S, or we worked it out in a previous section, and I'll use the exact value here for the 50, sample size of 50, 237 over 49. So I've got 237 over 49, that's S squared, divided by 0.25 squared. Let's put this on our calculator and see what we get. And that gives us 77.3877, so on. Now, n needs to be greater than that. It's a sample size, so n needs to be a whole number. So n needs to be at least 78. So 78 is basically our sample size. So if we took a sample size of at least 78 or greater, then we're going to get a standard error less than 0.25, which compares to a standard error of 0.311 when we took a sample size of 50. And the last thing, this is sort of just out of interest really, that in part A, if you were to work out the standard error, you would get this value here, about 0.40 to three significant figures. 0.400, and 0.396, and when it's 50, 0.311. So you can see as you increase the sample size, this standard error decreases. So you should now be able to do exercise 5A on pages 117 to 120. So here's first part of the recap. which basically just goes through what I did on the first slide, and this is the rest. So you could probably pause this or pause the beginning of the video and use that just to help you quickly go through the main points of this section.